brief explanation of what we have discussed last week, where the story is about homology, and the most important thing I managed to tell you was that okay, so in a nutshell, genes or proteins may be similar for a variety of reasons. And for us, the most important one is that they are homologous, meaning that they have common origin. And we've discussed at some length that this common origin could manifest as, well, the divergence after the common ancestor could be due to either speciation, and in this case, these genes are orthologs, and normally they retain their function. But it's not an absolute rule. Or the first event in their life could, after the common ancestor, could be duplication, and in this case they're called paralogs, and in most cases paralogs have different or maybe slightly different functions. More complicated, and normally if we see two genes in the same genome, they are parallel, but not necessarily, because the species in question is a result of a hybridization event, which happens in many cases, specifically, especially in plants. And in plants, it is often accompanied by polyploidy. So we get two diploid ancestral species, and after hybridization we have tetraploid descendant species, and in that case you might paradoxically observe orthologous genes in the same genome. And also genes may, orthologous or parallel genes might be observed in the same genome due to, for example, gene transfer, and it's a very important, actually, feature of a very important process in evolution, specifically, especially in prokaryotes, where horizontal gene transfer is very frequent, but also in eukaryotes, because we observe all interesting kinds of horizontal transfer in eukaryotes, like genes acquired by insects from bacteria, genes traveling between hosts and parasites, and so on and so on. I promised, and I forgot actually to tell you a story about orthologs that might completely change, no, not completely, but considerably change the function. My pet example is manganese transcription factor, manganese repressor in some outer bacteria, like Rhizobia species and the relatives. And the story is as follows. The ancestral protein was iron repressor, and it regulated lots of genes involved in iron metabolism, iron-dependent enzymes, and so on. And then suddenly, nobody knows why, in the ancestral species of, as I said, of Rhizobia and related groups, this protein, this transcription factor, has changed its specificity. And it has become the manganese repressor. Transcription factor that its cofactor was manganese, and it isn't regulating iron, genes involved in something with iron but instead it regulates the manganese transport. And how do we know it? Well, first of all, some people did experiments, and we also have done some computational analysis reconstructing this history. And what happened then, it's not a part of this story, but it's still amusing, that the niche of the iron repressor got freed. There were no more, because the former iron repressor had become a organic one. And now, there were actually competition between several transcription factors for genes of this iron regular. And in different groups, in different genera of the species, actually there are different transcription factors, all having the same function of iron repressors. So even if you didn't know that, we would very easily confuse this new, in some sense, new manganese transcription factors. Sorry, it's the third time I've made this thing slip off. For the iron one, because all its relatives are iron repressors. The only indication that something strange is going on would be that it is not regulating, the binding sites for this transcription factor are not observed upstream of genes working with iron, genes whose products work with iron, but rather upstream of this manganese transporter. But then, I would easily assume, again, if there were absolutely no experimental evidence, I would rather assume the change of specificity in the transporter than in compressor. So if we didn't know that, we might quite easily blunder into writing a wrong paper. For parallels, these things happen all the time. We've discovered that there are many possible scenarios, but the most frequent ones are sub-specialization where the common function is divided among new copies, newly arrived copies, or mere functionalization when one copy retains the old function and another copy gets a new function. And the most extreme example of this is crystallines forming the lens and in vertebrates. And these proteins are often recruited from former enzymes. Then we discussed at some length horizontal gene transfer and this problem that we actually we can easily reconstruct the history when only duplications and losses are involved. Because we can simultaneously minimize the number of duplications and the number of gene losses when we construct the optimal embedding of the species tree, of the gene tree into the species tree. But when we allow horizontal gene transfer, then we actually have a trade-off, because any tree could be explained either by only duplications and losses or by only horizontal gene transfers. And the more transfers we assume, the less duplications and losses we need, and vice versa. And we don't know the relative weight, the relative frequency of these events. Then we've discussed some, this slide, I wouldn't repeat that in detail, but we've discovered that there might be other indications of horizontal gene transfer, for instance, unexpectedly small similarity in genes from widely different species. If you have a human gene, which is a plant gene, which is 80% identical to the bacterial gene, then it's either a combination of horizontal gene transfer. It couldn't be normal evolution, because the common ancestor of plants and present-day bacteria lived billions of years ago. And the similarity should be very big. And vice versa, if you observe, we see homologous genes having the same function, but very different in closely related species. Again, it means that some of them have been got there by horizontal transfer. Now, finding horizontal gene transfer is difficult. It requires care, it requires construction of phylogenetic trees, and care for mediation over this phylogenetic tree. But there is fast and dirty way. The same as in finding orthologs. But I've told you that when you're looking for orthologs and you're doing it large scale, so you don't have time for construction of trees and looking at each tree one by one, you may use this fast and dirty bidirectional best fit criteria, which more or less, well, is in most cases is reliable. So if you're doing some mass analysis, then BBH is a reasonable empirical solution. And the same solution exists when we are looking for candidates for horizontal gene transfer, because basically, what does that mean? That your relatives are scrambled. But if a gene has experienced horizontal gene transfer, this history manifests as paradoxical relationships with genes from other organisms. And again, to repeat, the most reliable way to observe these paradoxes is constructing phylogenetic trees and identifying inconsistencies between gene trees and what we know about phylogeny. And the fast and dirty way is to run BLAST. I mean, everything fast and dirty involves BLAST, because BLAST is fast. And then you say that your gene has experienced a total transfer if other genes or other proteins more similar to yours do not come from closest relatives of the species you are working with. And now I'll tell you the story which I find amusing. It's a story about Metana sarcina species. Metana sarcina is a genus of Archaebacteria. Metana sarcinas are probably the species with largest genomes among of Archaea. And when the first Metana sarcina genome was published, people had identified these, used these three to identify horizontally transferred genes, because the expectation was that these additional genes, additional enzymatic metabolic capabilities come from bacteria. And to identify these genes that have been horizontally transferred from bacteria to Metana sarcina, people ran BLAST. And the gene was announced to be a candidate for horizontal gene transfer if its closest, most similar homologs were of bacterial origin. And it turned out that it had been estimated that about 1/3 or maybe 1/5 or 1/4, but a very considerable number, between 20 and 30% of genes in a variety of Metana sarcina species come from bacteria, are the result of horizontal gene transfer from bacteria. And this estimate was based on this fast technique of identifying horizontal gene transfer by running BLAST and looking at who is the closest relative, from which species the most similar protein comes. And we've been working on for a year actually on comparative analysis of transcriptional regulation in prokaryotes. And at some point, I thought that it might be fun to look at how these horizontally transferred genes are regulated. To look for binding sites. So the question was actually whether these horizontally transferred genes arrive with their own transcriptional regulators, like often happens, for instance, with systems for heavy metal resistance or antibiotic resistance. They travel on plasmids with their own transcription factors. Or an alternative is that the genes are acquired by horizontal gene transfer, but then follow under regulation of pre-existing transcription factors. So there are new binding sites arising evolution. And I thought that it might be, as I say, that it might be interesting to look at. And I've asked, actually, it was Sonia Goroshansk, who is your TA in this course and has been your TA in the bioinformatics course. So I've asked her to look at it. And what happened was that she couldn't find this 30 or even 20% of horizontal transfer because she has applied this. Let's keep the details. So yeah, what she did was a careful procedure. She identified homologous genes, took not the very first, the most similar homolog, but about 100 top hits, aligned them, constructed phylogenetic twists, and then she was looking for situations when metallocarbamide proteins cluster on the phylogenetic twist with genes within bacterial branches, within bacterial plates. And it was like 5%, which is normal. I mean, that's a key. It's normal in all bacteria have actually, in the history of all protein, families, at least one event of horizontal gene transfer has occurred. No protein, whatever its functions, is immune for horizontal gene transfer, including DNA polymerases, RNA polymerases, I don't know, ribosomal proteins, ribosomal RNA for that matter. It also can be horizontal gene transfer. RNA syndicated. So even genes with very core, very basic functions also might be horizontal gene transfer, can be actually horizontal transfer. So this 5% is like it's garden variety number. We see the same level of horizontal gene transfer in all bacterial genes. So nothing special about metallocarbamide. And then we started thinking about what can happen, why you don't see the remaining 20%. And I recall the story that happened when the human genome was annotated. If you look at the first paper on the complete draft version of the human genome, the paper published by the Human Genome Consortium, there's a paragraph on genes, on human genes for bacterial origin. And it was estimated that about 200 of human genes actually have recently been acquired, well, not recently, but at some point have been acquired from bacteria. I'm not counting mitochondrial genes. Well, genes encoding mitochondrial protein, that's a completely different story. And then this estimate was very quickly discounted because it turned out that the reason for that is as follows. Again, the same fast and dirty procedure was applied. So people actually run candidate human proteins against gene bank as of 2002. And whenever they saw a bacterial key but no eukaryotic keys, they assume that this is a predominantly cluster gene. But very few eukaryotic genomes have been known at that time. Human, Drosophila, yeast, mouse, no mouse actually, and that's it. And if a gene that has been present in LUCA in last universal common ancestor, in the common ancestor of all present-day genomes, if this gene, for some reason, has been lost by yeast, and there were lots of genes lost by yeast. Yeast, Rhamyces cerevisiae has a very teeny genome actually. And the same gene, for some reason, has been lost by Drosophila, and again, lots of genes have been lost by Drosophila. Then, this procedure would say that this is a bacterial gene in the human genome. So, what people did, other tests, they run this list of genes that are candidates for horizontal transfer. They run it against very raw data on the genomes of nematode Phenorhabditis elegans. So this genome hasn't been assembled yet. There were only raw reads, but these were sufficient to blast human genome against this list of suspicious human genes against the nematode data. And it turns out that the majority of these genes actually do have relatives, do have homologs in C. elegans. And these C. elegans homologs are much more similar to the human genes than bacterial genes, as it should be. And so there is no horizontal gene transfer, it's just losses in the yeast and in the Drosophila. And I thought that something like that might happen in this case. Because when the metanocarcina genome had been sequenced, a couple dozens of bacterial genomes have been known already, but only 1 or 2 archaeal genomes. And then we are in the same situation. We are comparing an archaeal gene with gene bank. But gene bank is mainly populated by bacterial genes. And it might easily be that this gene has been lost by the 2 or 3 archaea whose complete genomes have been sequenced by the time of that comparison. Whereas, when we have been redoing this analysis, there were already tens of archaeal genomes known. These genes, any metanocarcina gene was much more likely to have a known archaeal homolog being its closest relative. So what we did to check this hypothesis, and that's why I'm telling you this story, is that we have reconstructed the content of gene banks in different years. And then we have redone this analysis, actually not our analysis, but this blast-based analysis, and estimated, look at the top curve. So we've looked at the estimated fraction of horizontally transferred genes by this blast-based procedure, as if in 2001, as if in 2002, and so on and so on. And what we saw exactly this 1/3 of horizontally transferred genes if we were living in 2001, slightly less if we are living in 2002, and less and less and less. But the final estimate is still too high, because this blast-based procedure, as I said, it's not perfect, it's fast and good. So the real estimate should be somewhere around 5 to 10%. But still, we have demonstrated this steady decrease, and actually, this paper took 3 years to publish. text class, and lots of reviews, and most of them were highly unfriendly, because I think that we grappled quite a number of patterns with that. What I wanted to do was, well, actually, I wanted that the title of this slide is the title of the paper I wanted to, well, the title that I planned for this paper, but Sonia has convinced me that we shouldn't stick our nose too far. So the real title of the paper was much softer. But it still took, I mean, it still took, it was a struggle. So, next Monday, Sonia is having her final is having her PhD defense, and it's one of the chapters actually there. So it's a story with a happy ending. So what I'm saying actually that the take-home lesson from this is that even now, gene bank is not the perfect representation of the life diversity. Whatever are you doing, you should keep that in mind. For instance, well, one of the enigmas is that there are a lot of CRISPR cassettes and a lot of spacers not matching any known phage. And that's okay because we know much less than like 1/10 of a percent of all existing phages. So our sampling of the phage universe is very sparse. So keep in mind that gene bank is not the universe. Okay, that's it. And let's move to the next topic. That would be Pangenos. Pangenos. And again, let's start with some philosophy. And in this case, the philosophy is the definition of bacterial species. So what people normally do when they want to define species. Well, okay, two organisms belong to the same species, and if they can mate, and the progeny would be fertile. That's more or less textbook definition of species. But then there are some problems because you can have quite decent hybrids in plants, for instance. But more or less, you might have progeny that is not fertile, but it's not perfect either, like with human, probably has been the case with Cro-Magnon humans and Neanderthal humans. But by and large, this definition works for multicellular organisms that have sex. With bacteria, it's much more complicated. First of all, well, they do have sex in a sense because they have homologous recombination and all that stuff. But still, it's sort of irregular. On the other hand, we have very few morphological characteristics to classify bacteria. And in classic microbiology, bacterial species were defined based on morphology of cells and colonies, on metabolic abilities, so what these bacteria could produce, vice versa, what it could feed on, what compounds were necessary but could not be produced and had to be added to the media if you wanted to grow this bacteria, or maybe some chemical stuff like composition of the cell wall or chemical composition of the membrane, and that's it basically. Then the era of DNA has started, the era of molecular biology. And the new working definition of material species was that if you take DNA from one species, DNA from other species, denature this DNA, and then allow it to rehybridize in the mixture, then you would have more than 70% DNA hybridization. If that happens, if you observe that, then your two strains belong to the same bacterial species. Why 70%? Because there was a microbiology congress, and it has been decided that the threshold should be 70%. Actually, I think that the basis for this decision, I don't know, but it would be natural to assume that the reason for this decision was that it more or less fit to the previous, to all the previous taxonomy in microbiology. So with this definition, it was sufficiently formal. Now, but on the other hand, the threshold was selected so that not to reconsider all microbiology books. Okay, and then the era of sequencing has started, and the new definition was that two strains come from the same species if the level of sequence similarity in the gene encoding 16S ribosomal RNA is 97% or more. Again, why 97%? What was the God-given like enlightenment? Well, because again, with this threshold, microbiologists didn't have to reconsider all previous taxonomy books. But both set up, all these definitions are actually very arbitrary. Okay, and then the era of relatively cheap sequencing has started. People have sequenced 3 genomes of Escherichia coli. And it turned out, well, this is clearly one species. The level of the average similarity in common regions is, it says, 99%. Not in the ribosomal RNA, just in any region. No, maybe 98. So, but what happened was that lots of genes were present in 1 or 2 strains and missing in the remaining strains. Now you see it on the Venn diagram here. There were 3,000 genes common for all 3 species. But then the pathogenic species had additional 1,500 genes not present in the left strain. The left strain has the smallest number of these unique genes. That was because it looks like it has lost lots of genes during serial transfers in the lab or over the century. It has lost many genes necessary for pathogenic lifestyle. And basically, this actually explains very well the 70% requirement in hybridization experiments. Because what this means is that if you take 2 strains of E. coli, in each strain, about 70% of the genome would be homologous to the genome of the other strain, and about 30% would be unique. And then this unique,
all regions that are homologous are highly similar. As I said, 99 to 98%, 98 to 99%, sufficient for hybridization. So these common regions would hybridize and the unique fraction would not. And so it turns out that this threshold of 70% was actually selected rather wisely, even without knowing what's really going on. And then people have started looking at diagrams like that, and we see that even in this comparison, we have 3,000 common genes, common for all three strains. 1,000, approximately 1,000 genes present in 2 out of 3. And more than 3,000, 3,000 and a half are present in only one strain out of 3. And then people come with this idea of this concept of pangenome. And a pangenome is a total set of genes in all strains of a species, or it might be genus, or actually any taxonomy level. You might easily study pangenome of family, order, phylum, whatever. And the pangenome is divided into fractions, which is 4 the universal genes which are present in all or almost all strains. I will be speaking mainly on the level of species and genera. I'll have a couple of slides of more general nature towards the end of this lecture or this presentation. Unique genes which are strain specific or almost strain specific, so they're extremely rare. And a considerable fraction of these unique genes are actually results of misannotation. They are not genes at all. And another large fraction of these genes are genes that have been very recently acquired, pro-age genes, things like that, that have been very recently acquired and probably would be wiped out by selection in the next few thousand years, or maybe 10 years, whatever. So it's not very interesting. It's just like bubbles, evolutionary bubbles that arise and disappear. What is interesting, actually, probably the most interesting part of that is the periphery. The periphery are genes which are present in some strains, but not others. This brings us to another philosophical, to some extent, question, which is how bacteria evolve. Because normally we think of evolution as a tree. We have some ancestral species, then it divides, for instance, into Escherichia coli and Salmonella, and then each of these species separately divides into strains. So we think of evolution as a tree-like process. And actually I'm teaching you to think of evolution as a tree-like process. But in fact, it's not like that. We have a cloud of strains in the ancestor, and these strains shuffle their genes by homologous recombination. So there is some core. There are core genes which are present in all strains. There is this periphery. And somewhere are these unique genes, this cloud of unique genes. But then this speciation event means that this cloud of strains stops exchanging genes by stops exchanging genome fragments by homologous recombination. And so we see this cloud gradually dividing into two. But still some contrasts remain. Even if bacteria belong to different species, but still are related, there are more or less frequent horizontal gene transfer. So we have to look at evolutionary tree as very short-sighted people. Instead of this nice, beautiful tree with well-defined branches, larger branches or smaller branches, we actually have this fuzzy picture of strains exchanging genomes, having these core genes, which may be used to follow the evolution better, and having these periphery genes, which are frequently exchanged. And actually, at some point, we're still working on that, and other people are working on that. It's, well, I have a feeling that people much better understand the evolution of complex organisms like humans than the evolution of bacteria. So what we've done, we've taken available genomes of Escherichia, Shigella, and Salmonella, 3 genera of enterobacteria with many completely sequenced genomes. It's an old paper, so now we will have hundreds of genomes, or maybe even thousands, but then it was all we could get. And we started looking at these species in some detail. The first thing we've done, actually it's not the technique invented by us, but it's nice. So we had, well, one thing that we knew in advance was that Shigella is not a separate unit. It's a historical name, but in fact Shigella are all present-day Shigellas are actually Escherichia coli with some additional properties, and actually the genomes which are assigned to the genus Shigella, they even do not form separate clade on the tree of E. coli strains. They have these properties that distinguish between Shigella from Escherichia. They have arisen independently several times. So Shigella is not a genus, it's just misnomer. Okay, so if you take all available then Escherichia and Shigella genomes, then we could do this view plot, which reflects the following thing. On the horizontal axis is the number of strains. 1 strain, 2 strains, 3 strains, up to 32, which was the size of our sample. On the vertical axis is the number of genes present in exactly that number of strains. So we have core genome, the universal genes, on the right side of this plot. And it is like about 2,000 of such genes. And we have unique genes on the right side of that plot. And it's clear that it is a composition of several different distributions. There are actually 2 alternative ways to model this distribution. One model belongs to Kunin and Uriwolf, and they are decomposing such distributions into sums of exponents. So there is an exponent describing rare genes, an exponent describing frequent or almost universal genes, and in the middle, an exponent describing the periphery genes. Not universal, but still frequent. So basically, the belief is the model is that three more or less independent populations of genes, each having its own evolutionary dynamics. Or you can follow the example of linguistics and economics, where such distributions are described by power law. It's well known, for instance, that the frequency of words in a sufficiently large set follows the power law distribution. Well, reasonably well follows the power law distribution, and in linguistics it's called deep law. And economy, it is well known that the distribution of wealth among individuals again follows the power of law, and in economics it's called the Pareto distribution. And we thought that, okay, we can apply the same logic to genomes. And here we assume that there are two types of events. One event is occurrence of a gene. And for occurrence, we would have the power law because most genes would occur only once, less genes would occur twice, even less 3 times, and so on and so on. So this one power law would describe the left side of this distribution, or the other type of event would be non-occurrence of a gene. So by default, this gene would be present, and its absence again should follow the power law. So most genes in the second category would be present. Fewer would be absent in one strain, even fewer would be absent in 2 strains, and so on, again and so on. So we decompose this distribution into sum of 2 power laws. In this particular case, we have pure 3 parameters, 4 instead of 6 as in the sum of 3 exponents. But the thing is better. So we were actually very excited that we have the better description, that we have tweaked the nodes of the great Kunin. It turns out that the life is not as nice as we wanted it to be, because for other genera, actually the sum of 3 exponents works better. So my present hypothesis is that actually there is a shift between 2 modes of evolution, and at very close distances, the power law works better, and at larger distances, the Kunin model of 3 exponents would work better. And again, when we are looking, so now we observe actually both types of behavior. And I do think that it might be, but we need to do it carefully, but I do think that it might be related to the degree of relatedness of traits you are looking at. So this is what happens if we run this procedure, if we construct this U-curve for single species, for strain that clearly belong to the same species, exchange genomic information, and are in the sense of self-contained in a sense. But what happens if we mix two different genera, for instance? Like in this case, what happens if we mix Escherichia and Salmonella? We get this ugly internal piece. And why do we get them? Because we do have some genes which are universal in all sorts. Basically, it's an overlap of three different U-curves. The largest one describes the behavior of common genes. And on the top of that, we have two additional U-curves describing genes which are present in Salmonella, and some of them are universal for all Salmonella species, but completely absent in Escherichia. And vice versa, you might have genes which are universal in Escherichia and completely absent in Salmonella. And so these internal peaks indicate that our sample, our set of strains, is not homogeneous. That there are genes which clearly distinguish, differentiate one species from that. And actually we'll return to that a bit later. Now, how does the core genome behave? Well, the core genome, the size of the core, well, now this is what was plotted here. The number of strains is on the horizontal axis. And the size of the core genome estimated given that number of strains is on the vertical axis. And the error bars just denote what happens when you make multiple subsamples from your final set, your main set of strains. Now, what we see here is that the core size is decreasing. There are several different plots here related to slightly different computational procedures. That doesn't matter much. What you may observe is that, first of all, the core size shrinks, which is natural because when you add a new strain, there is no way you could increase the core. Each new strain might miss some of the core, some of the genes from the previous core, but it might not add something to the core, by definition. So the core are genes present everywhere. And it's still shrinking when you add new genes, but actually, for most species, again, as I said, it's an old paper. What we see now is that after like 50 or something strains, the core size stabilizes. It reaches saturation. So if you define the core looking at 100 strains, that would mean that the same gene would be almost all, maybe excluding some unique cases, but basically all these genes would be observed in the next 100 strains. The pan genome, the set of genes present in all strains, increases, and in most cases, for all genera we've studied actually, it is not reaching saturation. So each new strain brings the same number of new genes as previous strain. Which is sort of well, you may not study systems like that, because whatever is the number of strains we have already looked at, it's clear that your sample is not covering the entire universe, the entire set of genes present in this strain. This is bad news. Good news, one of our inventions at Stockholm crowd is as follows. This definition of pangenome, where you count every gene, actually is not a good one. And the better definition would be, the better technique, a better way to look at that would be to count the number of genes present in a fixed fraction of traits. So what is plotted here is, again, the number of strains is on the horizontal axis, and the number of strains present in that fraction of the number of genes present in that fraction of genes of strains of genomes is plotted by shades of gray. Now, just ignore the zigzag pattern. They come from the fact that we are dividing integer numbers, so it's an artifact, an arithmetic artifact. So we have the core here, universal genes present everywhere. And for instance, the middle line, this one, is the fraction of genes present in half of your strains. These are almost universal genes, which are present in 90% of your strains. The topmost one is the pangenome, and the second from the top is genes present in at least 10% of strains. And it turns out that all curves except the pangenome size actually get saturated very quickly. So after whatever is the number of strains you're looking at, you may safely bet that about 4,000 genes would be present in half of these strains. It could be different halves, of course. For E. coli. For other genera, of course, these numbers are different. So again, what we see is this cloud of genes with core, frequent periphery, rare periphery, and unique genes which are not interesting. And the size of these various parts of core and periphery are actually fairly stable. They can be estimated from just a few strains, which makes this entire area much more amenable to some reasonable analysis. And now, now we'll make a break, and then I'll continue with even more beautiful two-dimensional picture.